This is the majestic landscape and waters that surround the Susquehanna River, one of the oldest rivers in the world. Despite its beauty, the Susquehanna River and the Chesapeake Bay downstream has been facing the detrimental effects of excess nutrients. So what exactly does the science say when it comes to the water quality in the Susquehanna River? Well, let's find out. The Susquehanna River is the longest river on the east coast of the United States, flowing 447 miles from Cooperstown, New York to Havre de Grace, Maryland, and then continuing another 180 miles through its ancient river valley, now drowned by the Chesapeake Bay, and then finally exiting to the Atlantic Ocean, draining a total land area of approximately 27,495 square miles. Compared to the other major drainage regions of the Chesapeake Bay watershed, the Susquehanna River drains the largest land area and contributes the most stream flow to the bay, having strong control over the health of the Chesapeake. Before the 1800s, the Susquehanna landscape was covered by a vast forest with patches of indigenous agriculture. In a relatively short period of time, the clear cutting of forests made way for the growth of towns, farms, mining, and industry. After World War II, forests began to grow back, but continued population growth led to the expanding development and intensification of agriculture that are familiar today. All of this change released massive amounts of legacy nutrients and sediment into the valleys and streams that still remain a challenge. To combat the detrimental effects of excess nutrients, pioneering legislation and restoration initiatives on the regional and state level were put into place to address the increasing concerns over the human impact on the water quality of the Susquehanna River and the Bay. So what is the problem we currently face? Well, we all need clean water to drink. In fact, over 4 million people live around the Susquehanna River and rely on private and public water supplies. Nutrients and associated contaminants from developed and agricultural areas can increase the treatment costs for public water supplies and can threaten private, homeowner wells in rural communities. Fish and other aquatic organisms need clean water too. Unfortunately, 67% of the impaired waters that drain to the Susquehanna River don't meet aquatic life criteria due to nutrients and sediment. All of these excess nutrients, nitrogen and phosphorus from the Susquehanna and other tributaries that reach the bay, feed algae growth and decay, and have created increasing hypoxic dead zones of low oxygen for fish and other estuarine life. Before we go any further, let's define some important terms. First, a watershed is the land area that drains rainfall to a water body. Concentration refers to the mass in a known volume of water, whereas the load is the mass delivered over a given time, and the yield is the load relative to the contributing landscape. Actual nitrogen loads vary widely with annual river flow, so to remove the variation, a flow normalized load technique is used to better see the overall trend or progress towards water quality goals. If you could picture the amount of phosphorus without the water that comes down the Susquehanna and its tributaries in the single year of 2020, it might look like this. Phosphorus tends to bind to soil or sediment particles, and there is about 3 million pounds that is not trapped by the largest downstream dam, Conowingo, but is still able to pass through the Chesapeake Bay. This is equivalent to about 111 dump trucks of phosphorus. For the same year, we can picture the movement of nitrogen down the Susquehanna and its tributaries. Since most of the nitrogen is dissolved in water, about 107 million pounds is able to pass through to the bay. This is equivalent to about 3,567 dump trucks leaving the Susquehanna watershed in that year. Lastly, sediment plays a major role in nutrient transport and can be an impairment as well. Despite some of the sediment being trapped, about 1,380 million pounds still leaves the bay, enough to fill a massive 46,000 dump trucks of sediment. Compared to the other major rivers, the Susquehanna carries the most nutrients and sediment to the Chesapeake Bay. Trends in phosphorus exported from the Susquehanna to the bay started to increase in the late 1990s to about 2012, followed by a slight decrease over recent years, still above the water quality target. the load of nitrogen showed a promising decline in the 1980s, but loads have remained consistent in recent decades. The late 1990s also saw a dramatic rise in sediment that started to decrease in recent years. So what are the current trends we see in nutrient water quality around the watershed? Let's start with nitrogen. Besides lightning, in natural ecosystems, most bacteria converts nitrogen from the atmosphere and then back through denitrification. Under modern conditions, inputs from manufactured fertilizer, manure, development, wastewater, and atmospheric deposition can exceed the capacity for denitrification to convert nitrogen back to the atmosphere, and surplus nitrogen often moves as nitrate through groundwater to streams. Here you can see that nitrogen yields from the land are greatest from the central and southern area of the watershed, with more intensive agriculture and urban development. Thanks to several long-term monitoring stations, we can also see all the nitrogen, in this case 2012, that begins to accumulate down the river from the North Branch, West Branch, and Juniana. The nitrogen from these branches and other tributaries comes together in the lower Susquehanna before making its final journey to the bay. 2012 is just 1 year for which we can see nitrogen loads. Overall, nitrogen loads, primarily driven by nitrate at the Towanda monitoring station, have shown a steady decline from 1985 to 2011, but are relatively constant more recently. The most significant factor that drives trends in nutrient load in streams and the river are the sourced inputs, such as fertilizer, manure, wastewater, and atmospheric deposition. For example, the improving trend in nitrogen load at Towanda are likely driven by the reduction of total source inputs since 1985. Across all the long-term sites, trend in stream nitrogen loads have been improving, indicated by the blue arrows, and total nitrogen source inputs have been declining, primarily driven by reductions in atmospheric deposition and wastewater. Additionally, manure inputs have declined in the North Branch at Towanda and Danville, but have increased along the Juniana at Newport. Overall, long-term trends in stream nitrogen loads are improving, but this is not always the case for more recent short-term trends. In fact, short-term trends show that 54% of the sites have improving or no trends, but 46% are degrading. Some of the degrading trends are in the North Branch, West Branch, and as you move down the main section, but the lower section of the Susquehanna shows improving trends. Shifting focus, phosphorus comes from similar sources such as fertilizer, manure, and development, but originates from natural erosion and phosphate mining, largely from outside the watershed. Phosphorus can move in dissolved form and accumulate and leach from soils, but is mostly found in particulate form attached to sediment and transported during storm events. Therefore, it's important to understand sediment transport through runoff from deforestation, resource extraction, such as mining, construction, development, impervious surfaces, and agricultural practices. Additionally, sediment and bound phosphorus can be eroded from stream banks, but also stored in floodplains, stream channels, and behind dams to be dispersed again to the streams, river, and bay during storm events. There is no natural process to remove sediment-bound phosphorus, so it's often recycled in the aquatic environment. Similar to nitrogen, phosphorus yields are greatest in areas with more intensive agriculture or urban development. And at long-term monitoring stations, phosphorus in 2012 accumulates downriver from tributaries to the bay. Trends in stream phosphorus loads at long-term sites have been improving, except for Towanda with no trend. Source inputs for phosphorus at all sites declined except for Juniana at Newport, with stable fertilizer and increasing manure trends. Overall, long-term trends in phosphorus are either improving or have no trend. Short-term trends, 2011 to 2020, show that 12% are degrading and the rest improving or no trend. As you move down the watershed, most short-term trends are improving, have no trend, or have minimal degrading except for Towanda. Now, let's explore deeper the factors that affect nutrient water quality in the Susquehanna. Let's start out with the physical factors like geology, climate, and hydrology that have a lot of control over water quality. For a relatively small geographic area, the Susquehanna watershed exhibits a spectacular and diverse geological setting spanning hundreds of millions of years that has a strong influence on the water quality and transport of nutrients and sediment to the river. On top of all this bedrock, there is a small layer of sediment and soil that groundwater also travels through. For example, in the north, the advance and retreat of glaciers profoundly shaped the landscape by carving out valleys, leveling hills, and depositing glacial sediments. Overall, on average, groundwater accounts for 60% of stream flow, and it takes time for groundwater, pollutants, and the effect of management actions to reach streams, often referred to as lag time, that can range from days to years in the southern portion of the watershed or much longer in parts of the north. Several areas of the Susquehanna watershed are susceptible to contamination from nutrients, such as nitrate in groundwater, that many residents depend on for drinking water. And excess nitrate and associated pollutants can be a health risk. Let's take a closer look at groundwater in Clinton County, Pennsylvania, that has a mix of rock types. Many groundwater residents get their drinking water from wells drilled in the sandstone and shale aquifers, where nitrate concentrations are close to zero. Some get it from the sand and gravel sediments that are more porous and can transmit higher nitrate. Others draw water from where nitrate infiltrates most rapidly, in the limestone and dolomite aquifers through the sinkholes and voids, where the median nitrate was 3.26 milligrams per liter and can be as high as 49.3 milligrams per liter, way above the federal threshold for drinking water of 10 milligrams per liter. Groundwater is also connected to streams, and this can be complex in agricultural, carbonate areas implementing conservation practices. In Fishing Creek, in the southern part of the county, there is a substantial loss of the upstream flow and nitrogen load underground through sinkholes, and the stream goes dry until most, but not all, of that water and nitrogen reemerges through the large springs to the downstream. The varied climate and hydrology throughout the watershed is another major factor affecting the delivery of nutrients to the Susquehanna. The higher elevations in the north and west have cooler average temperatures and generally receive less precipitation, except where air moves from low to high elevations and cools more rapidly. Heat trapped by greenhouse gases causes more evaporation in the summer and the fall, and precipitation in the winter and springs, causing increased storm events and runoff, scouring the release of legacy nutrients and sediment. A milder climate is expected to produce increases in population, provide for longer growing seasons, greater demands on groundwater recharge, and earlier algal blooms in the bay. For example, continued warming trends are projected to produce less snowpack and earlier runoff in the winter versus the spring, followed by less of a change in runoff during the summer and fall. These seasonal shifts in surface runoff will affect the nutrient and sediment export to streams. Stream flow can vary over the long term, but following the 1960s drought, stream flow in the Susquehanna suggests more wet years and greater variability in more recent years. Additionally, stream flow can vary over the short time scale during major episodic events. For example, the Susquehanna River received a catastrophic blow from the tropical storm Agnes in 1972, which delivered the maximum amount of stream flow ever recorded to the bay, together with large amounts of nitrogen, phosphorus, and sediment. During similar major storm events, like Hurricane Ivan in 2004 and Lee in 2011, the concentrations of nitrogen and phosphorus were among the highest ever measured at Conowingo Dam. Let's talk now why source inputs from the atmosphere and land are the most important factors affecting nutrient water quality. Inputs from the atmospheric deposition of nitrogen originate from emissions from power plants, vehicles, and agriculture, and are widespread across the Susquehanna River. The highest values occurred in developed areas, such as urban centers and areas of intensive agriculture, such as in southeastern Pennsylvania. Overall, inputs have been declining across the watershed thanks to the Clean Air Act. For example, decreases in atmospheric deposition have resulted in the reduction of stream nitrogen load in the forested Pine Creek watershed in Lycoming County, Pennsylvania since 1985. Besides the air, overall inputs are greatest from land activities. Land use in the Susquehanna watershed is predominantly undeveloped, followed by agricultural and developed areas. land use in the north is different than the south. In northern areas, like in Susquehanna Creek in Wyoming County, there is more forest and mixed land use types with a smaller, consistent agricultural footprint and a declining number of farm animals, with the exception of beef cattle and horses. Whereas places in the south, like in the Quittapahilla watershed in Lebanon County, much of the forest has been converted for agriculture and increasing development with the intensification of all varieties of animal production in key areas with increased fertilizer and manure use. For example, there has been a substantial increase in the number of broiler chickens sold in Pennsylvania from 1954 to 2012, and incorporated selected breeding and nutrition improvements have more than doubled the weight of broilers. Fortunately, there has been an increase in the variety and quantity of conservation practices to reduce nutrients from agricultural areas. Eventually, nitrogen reductions are expected across the Susquehanna watershed for conservation practices and land retirement. For example, Hungry Run is a small agricultural watershed with enhanced efforts to implement conservation plans, restoration, and infrastructure expected to substantially reduce nutrients and has already seen improvement in aquatic life. Efforts to better monitor smaller agricultural watersheds is underway around the watershed. Monitoring stream flow and nutrients like nitrate will provide real-time concentration and loads to better evaluate progress and drivers of water quality. Developed areas contribute nutrients and sediment to waterways through wastewater, impervious stormwater runoff, lawn fertilizer, pet waste, and stream erosion. If population trends continue, then future growth throughout the Susquehanna watershed will be focused in suburban and adjacent counties, with an emphasis on large lot, single-family homes. Land use change can have a major effect on the nutrient load. For example, nutrient loads to Conestoga River have gone down from 1985 to 2020, while the percent land use has decreased for development. In many developed areas, nitrogen from wastewater plants like in Binghamton, New York, have declined, controlled through regulation and enhanced technology, and will likely continue to be important in controlling nitrogen loads in urban streams. Additionally, resource extraction has left a footprint on the land. Thousands of unconventional vertical oil and gas wells have been drilled over the past 150 years, predominantly in the western part of the Susquehanna watershed. More recently, over the past decades, unconventional wells drilled horizontally have expanded further east. For example, Bradford County, among all the counties in the Susquehanna watershed, has the most horizontal unconventional gas wells drilled, and the related infrastructure, well pads, pipelines, and so forth, has become a relatively recent part of the landscape. Historically, though, during the 18th and 19th century, coal was king, and its mark remains in places like in the Wyoming Valley. When anthracite coal was mined, support pillars helped prevent collapse, and boreholes were drilled to keep water out of the mines. Waste rock was left behind and continues to be a source of sediment to streams and the river today. As coal mining slowly began to cease and the pumping stopped, water filled the mines and acidic water rich in metals began to drain to nearby waterways. The Knox mine disaster marked the beginning of the end in the valley when the Susquehanna River broke and over 10 billion gallons of water flooded the mines in 1959. The mining legacy has left over 1,305 miles of streams impaired by acidic mine drainage, and extensive restoration efforts have helped reduce sediment and neutralize the impacts such as low pH on water quality. In fact, the acidic water of the 1950s has improved to near neutral in the 2000s, and even slightly alkaline more recently. Phosphorus in the Susquehanna River may be tied to legacy sediment and changing pH. For example, at a lower pH of 5 to 7, lower amounts of orthophosphate is released, but greater than a pH of 8, more phosphate could be leached and dissolved in the water column and feed excess algae growth. So lastly, we cannot forget to talk about how much legacy storage is a factor affecting water quality. Non-point sources applied to land may run off, but also accumulate in the soil and groundwater, taking years to decades to reach streams. In fact, 47% of the current nitrogen load of the Susquehanna can be attributed to legacy sources, and the rest attributed to the current year. There is also a lot of legacy nutrients bound in sediment from past land use activities that can be released downstream. For example, an old mill dam can hold back centuries of sediment and nutrients. And the cumulative effect of all the old mill dams can really add up to potential sediment and nutrient release, especially during storm events. Dams like the Conowingo, part of the lower Susquehanna River, is an example of a large impoundment that can only hold back sediment and nutrients so long before reaching capacity. There are 633 dams throughout the Susquehanna River network that are trapping sediment and particulate nutrients, but the three most downstream large hydroelectric dams are of most concern to the bay. Safe Harbor filled around 1950, followed by Holtwood in the 1960s, and finally Conowingo in the past decade. This lower reservoir system of the Susquehanna is essentially at full capacity and is no longer a long-term sink, helping to prevent sediment-associated nutrients from entering the Chesapeake Bay. So with a better understanding of the trends and factors affecting nutrient water quality in the Susquehanna watershed, what do we really have the most control over? Well, we have less control over the regional effects of climate, population, atmospheric deposition, and the extent of land use, but we have more control over the local management of our current and future land use and wastewater discharge. Considering management's capacity in controlling change and the movement of nutrients are important components of a successful nitrogen reduction strategy. The Susquehanna is a reflection of how we've managed the landscape around us, and over time, the river will bear a likeness based on our continued stewardship.